Hey folks, we're going to talk about elastic collisions and do a problem with them. This is a quick summary of the three types of interactions that you might have. So the first kind was explosions. And for explosions, momentum was conserved. Okay, momentum's always conserved if you make your system big enough. But kinetic energy was lost. I'm sorry, was gained. Kinetic energy was gained. So there was the two carts in the spring. When the spring unloaded, it let the carts go. The carts gained energy from the spring. The second kind of collision we talked about was inelastic. That's when two things start apart and together. And in that case, kinetic energy was lost. As a matter of fact, in the example we did previously, we calculated that for the example we did. And for our example, we lost 99.9% of the kinetic energy and it became heat. Okay, so that's inelastic collisions. But however, momentum was conserved. Again, momentum is always conserved if you make your system big enough. Now, the third type of collision is called elastic. And that's where two things start apart and end apart. They bounce off each other, okay? And the very, very classic example of that is a pendulum swinging. So let's take a look at that, okay? And here they're going to start with letting one ball go, and it takes one ball to come off. Okay? And then now they're going to have two balls and two balls. Okay? And then they're going to try three balls and three balls will be used, and so on. Okay? So, what's going on with that? Okay? Well, there's two things happening there. First of all, momentum's conserved. However, how come when, for instance, let's say they had one ball come in with a speed v, so it has a mass m and a speed v, and then here are the other four balls, okay? How come two of them can't break off? So that would be a 2m and go a half v, okay? How come you never see that here? Okay, now first of all, would momentum be conserved? Well, yeah, you'd have an mv beforehand and you'd have a 2m times a half v after, which is still mv. So that would not violate our conservation momentum law. However, you are violating something else. It turns out elastic collisions are special. Not only is momentum conserved, hey, it always is, but something else is conserved as well, and that is kinetic energy. If you look at this example, if this were to happen, what would we have? So over here, we'd have 1/2 mv squared. Over here, we'd have 1/2 times 2m times a half v squared, which would turn into 1/4 mv squared. We would have lost half of our kinetic energy to make this happen. That doesn't happen. That doesn't happen because not only is the momentum conserved for these collisions, but so is the kinetic energy. So now we have, for these kind of collisions, we have two tools in our toolbox. Now, the next bit I'm going to do is I'm going to derive an equation for you. If you want to skip the derivation, you can. I will write a big star on the video, and when you see that big star, you can unpause or unfast forward it and listen to the verbiage after. And I'll kind of summarize what I did for the derivation. But the derivation itself isn't all that important, but what goes into it is, and I'll explain that at the end. So here's a derivation for you. Let's say we know momentum's conserved. So let's have two objects, A and B. And let's say they start off with an MA and a VA and an MB and a VB. And they interact, they collide. And afterward, they have an MA and a VA prime and an MB and a VB prime. Okay, so this is conservation of momentum. The total momentum before is the total momentum after, okay? Now, I'm going to play with that equation a little bit. I'm just going to move the A's to one side and the B's to the other, and then factor out the M's. So on the left side, you'd have an MA times VA minus VA prime. And on the right side, you'd have an MB times VB prime minus VB. Okay, so I just move stuff around a little bit. And that's the same equation, just factored out. Now we also have, because this is an elastic collision, conservation of kinetic energy. So the kinetic energy before is going to equal the kinetic energy after. Now that's a little more complicated. Now you have this 1/2 mv squared stuff. So you got 1/2 ma va squared plus 1/2 mb vb squared equals 1/2 ma va prime squared plus 1/2 mb vb prime squared. Okay. Now we're going to do the same thing. We're going to move all the a's to the, we're going to cancel the halves out. Let's start with that. And then we're going to move the a's to the left and the b's to the right and factor out the m. So we got ma va squared minus va prime squared equals mb times vb prime squared minus vb squared. Okay. Now, if you look at that second equation, if I have x squared minus y squared, you can factor that out. It becomes x minus y times x plus y. So I'm going to do that here. So we got ma va minus va prime times va plus va prime equals mb times vb prime minus vb times vb prime plus vb. Okay. Now, if you look at the conservation of momentum equation and you look at the conservation of kinetic energy equation, you're going to see a lot of similarities. Now, here's where we get some fun math. What we're going to do is we're going to divide the kinetic energy equation divided by the momentum equation. And if you do that, the m's all cancel out and the minus terms all cancel out. And what you have left is VA plus VA prime equals VB plus VB prime. All right. And if you get the original speeds on the left and the final speeds on the right, most textbooks will write it something like this. They'll write VA minus VB equals negative quantity VA prime minus VB prime. Okay, now there are other ways you can write that, but that's what you're going to see in most textbooks. Okay, so now I'm going to write that big star for those people that fast forwarded through their this part of the derivation. I'm going to write that big star for you. Okay, so here's what's important about this. I call this the shortcut formula. Here's what's important about it. It only works for elastic, only elastic. And it comes from the following two ideas. Momentum is conserved and kinetic energy is conserved. If there's a test or anything like that, or you're asked about this, you need to know that this comes from the idea that not only is momentum conserved for elastic collisions, but so is kinetic energy. Okay. Now, let's use this in an example. So let's say I've got the following example. I've got a track, and I've got a little cart. His mass is little m, and he's moving with some v naught v. And he's going to collide elastically, so he's going to bounce off of a big cart. And here's what I want to know, very simple. How fast does v naught have to be to make big M make it through the top of the loop without falling out of the loop? Okay. Now, there are three locations here. There's A, which is before they collided. There's B, which is after they collided. And then there is C when the big cart is at the top of the loop-de-loop, okay? So let's start with C. Now, if I look at only location C, well, there I'm going to use Newton's second law. I'm going to draw an FBD. So here's our cart. Two forces act on it. Force of gravity and force normal, okay? And net force equals MA. Now, I'm going fast here because it's review. So we got Fn plus Fg equals m, and it's going in a circle, so that's v squared over r. Oh, and let me give you that one last bit of data. Let's say I give you the radius of this loop, and let's assume for the sake of argument it's circular. Okay. At min velocity, Fn approaches 0. In other words, it's just making it around the track. The tires are skidding against the track and just barely making it. So now this equation becomes Fg, which is simply mg, equals mv squared over r. Now I can cancel my m's out, and I get v min up there is root gr. Okay, so that's review. So that's the min velocity this cart's got to have up there to make it around the loop without falling out. Okay, so now I'll look, let's say A to B. Well, for A to B, I've got two objects interacting, bouncing off each other. Okay, so for that, I'm going to use conservation of momentum. The total momentum before is the total momentum right after the collision. Okay. Now, having said that, we've got the little cart before. moving at v naught, which I'm trying to find. The other guy is still to begin with. After they collide, we've got the m. I'll call this v1. That's the little guy's velocity after he hits the big dude. Plus we got the big M, and I'll just call that v. Okay. Now we got three unknowns here. I don't know v naught, I don't know v1, nor do I know v. Okay. But because this is an elastic collision, I can use my shortcut formula up here. Okay. A being the little guy, B being the big guy. All right. So let's try that out. So little guy is v naught, big guy is 0 before they collide, and then equals negative. After the collision, we've got v1 little guy minus v of the big guy after the collision. Now, I still got three unknowns, and I still only have two equations, but now I'm at least gotten somewhere. So in this blue equation here, I am going to do a little algebra. And I'm going to get rid of the v1. I'm going to solve for v1 and sub it in there and get rid of it. I don't care what the little dude's velocity is after they collided. I'm not asking for that, and I don't care. So if I solve for that here, it would be v minus v naught. And I'm going to sub that in right there. Okay. So we got m v naught, little m v naught, equals little m quantity v minus v naught plus big M v. Okay, and let's solve for v naught. So we got little m v naught equals little m v minus v naught. Now remember, v, that's the velocity of the big dude after they collided, plus mv. I just rewrote that, silly me. All right, let's put this in here, mv minus little m v naught plus big M big V. Okay. If we take this and move it to the left side, this becomes 2 mv naught. And on the right side, I've got little m plus big M v. And if I solve for v naught, I get little m plus big M times the v. Now again, that v is the velocity of the big dude right after the collision over 2 little m. So I'm pretty close here. I've got an equation. The only thing is I don't know what big V is. I don't know what the velocity of this dude right after the collision is. So that's where I'm going to look going from B to C. Okay, I'm just going to look at the big dude going from B to C. Well, when big dude goes from B to C, energy is conserved. We're looking at one object moving from one point to another. So we're going to use our conservation of energy equation. So U at B plus kinetic energy at B plus any work done by non-conservative forces equals U at C plus kinetic energy at C. Okay. At point B, he's at ground level. We're going to call that zero potential energy. The only non-conservative force acting on him, by the way, we're ignoring friction. The only non-conservative force acting on him is the normal force, which at all points is perpendicular to his motion, so it's not doing any work. So that term is also 0. So I'm left with 1/2 big M v at B squared, which is our big V, equals mg, big mg. The height is the diameter of the loop, which is 2 times the radius, plus the kinetic energy at C, which is 1/2 big M. And the velocity at C is root gr. So if I square that, I get gr. Okay. Well, if you look at this, the big M's drop out, and I got 1/2 v squared equals, I get a 2 gr here and a 1/2 gr there. So it's 5/2 gr. So v is square root of 5 gr. That's the velocity that's the minimum velocity this big dude's got to have to make it around the loop without falling out. Okay. So that simply goes right there, and that's your answer. So v naught equals little m plus big M root 5 gr all over 2 little m. That is the minimum starting velocity of the little dude so that he'll bounce off the big dude and make the big dude go around the loop without falling out of the loop. Okay. Now, this might be a problem where if you had numbers, it might be even easier to use the numbers on this, but it's good algebra practice to do this without the numbers. So again, big picture on this. For elastic collisions, not only is momentum conserved, but so is kinetic energy. And we have a shortcut formula derived from those two ideas. If you take these two equations and do a little math, you get what I call the shortcut formula, and we can use that, but only in elastic collisions. Please do not attempt to use this in inelastic or explosions. It will not work. You will get the wrong answer. So I hope that was helpful, and thank you very much.